Okay, hello and good afternoon. So today we'll talk about the one implementation of reader-writer lock, and potentially we'll have, if you have time, we will analyze it. Now, what is a reader-writer readers-writers lock? So I'm going to motivate that with an example. So suppose that you have a database. And in this database, you have a bunch of threads that are just readers of this database. For example, in a search, web search, whenever you get a query, you're going to just go and read from your database. And then you probably have these threads that crawl over the network and update the database. So there are threads that are writing to the database and potentially maybe reading from it. And then there are threads that are just purely reading from the database. Now, this database is a shared data because a bunch of threads are accessing it. Now, what we want is the readers should be able to read as long as there are no writers. So you can have multiple reader threads access the database simultaneously without having data race, because these are just reading from the database and it's safe to read. Now, if a writer has access to the database, then you don't want any reader to have access or any other writer to have access. So we want mutual exclusion when there are writers, and we are fine with multiple readers to have access to the database simultaneously. So putting it all together in this table, here we are considering two threads. You can expand on this. The rows of this table represent thread 1, and the columns represent thread 2. Now, in the case where thread 1 is writer and thread 2 is writer as well, we do want mutual exclusion. So they cannot have access at the same time. If thread 1 is a writer and thread 2 is a reader, then we again want mutual exclusion, so they cannot access the database at the same time. If thread 1 is a reader and thread 2 is a writer, again, we want mutual exclusion. But if both of them are readers, so if thread 1 and thread 2 are readers, then we're fine with them accessing the database at the same time. It's okay. Now, we want to implement a lock to do this for us. So what do I mean? So far, what we've seen during the lecture, we've seen mutexes, we've seen semaphores, we've seen monitors. Now, none of them can do this for us because these are designed for mutual exclusion. So one thread has access, the other thread doesn't have access. Now, because of this property here, that we want readers to be able to access the database at the same time, we cannot use these guys out of the box. So instead, we're going to design this class. We can call it reader-writer lock. So we're going to design this class, and we can use these primitives in our implementation to design this class. So this lecture is going to be about designing this class and implementing it. Now, here is the API of this class. let's just start with the public operations that this class supports. So the first one is acquire RL. So this acquires this lock as a reader. And then we want to release this lock if we are a reader. And then we have acquired the lock as a writer and release the lock as a writer. So these are the functions that we want this to have. So if you are a writer thread and you want to access the database, you are going to use acquire write lock. And once you're done with accessing the database, you're going to release the write lock. If you are a reader thread and you want to just read the database, you acquire the reader lock before you access the database. And once you're done reading, then you release the reader lock. So that should be hopefully clear. So these are the functions that we want this lock to have. Now, to implement it internally, we're going to use a mutex. So this implementation, you probably can do, not probably, you can definitely implement this class using semaphores. But as we discussed previously, we're not going to use semaphores. So we're just going to use monitors. Now, for this monitor, what do we need? A monitor consists of a mutex. So this is going to be a mutex that we're going to use. We're going to have two condition variables, one for OK to read. So if it is not OK to read, let's say if there is a writer thread accessing the data, and I'm a reader thread who wants to access the data as a reader, so I have to wait. So I will use this OK to read condition variable to wait. So I call OK to read that wait to go to sleep if there are writers. And then if I'm a writer and a bunch of readers now have access to the database and I have to wait for them to finish, then I wait on OK to write condition variable. So these are the two condition variables we're going to use for scheduling constraints. And the mutex we're going to use for mutual exclusion. Now, this is the part that is the most important part. This mutex, we're not going to use this mutex to access the database, right? This mutex, we're going to use it whenever we want to access the internal data of this class. Now, what is the internal data or internal fields of this lock class? Well, these are the four that we are going to use in this implementation. We're going to count the number of active writers, the number of active readers, the number of waiting writers, and the number of waiting readers. So you are active writer if you have access to the database. So it means that you have acquired the lock. So if as a reader, you acquire the read lock, you become active reader. If as a writer, you acquire the write lock, then you become active writer. If you try to get acquire the lock as a reader, and let's say another writer has access to it, then you have to wait. So you become a waiting reader. Or if you want to acquire the lock as a writer and there are some readers, then you become a waiting writer. Okay, so to recap, this class, we're going to implement it and then give this to our programmers who are going to write the program that is going to access the database. So for programmers who are going to use this class, they don't care about any of these private data. So they don't know if there is a mutex here, if there are condition variables, they don't care, right? So if you're a programmer that is going to use this reader-writer lock, you don't care about the mutex, the condition variable, the active reader-writer. These are, you don't care. All you care about are these functions. So if you are writing a thread that wants to be a writer to the database, you have to use this acquire writer lock at the beginning of your function, and then release it at the end of your function once you're done writing to the database. So from the programmers who are going to use our class, they just care about these functions. They're going to use it. Now we're designing this class, we're going to care about these and managing them properly. And for us, this becomes our critical section. So there are two critical sections in this case. One critical section is for the programmer when they want to access the database. So the database is the critical section, is the data that you want mutual exclusion for. So that's for programmers. We don't care about that. For us, the critical section is whenever we want to change the state of this lock. So we care about this. So we want mutual exclusion on these variables. Every time we want to change active readers or active writers, or waiting readers or waiting writers, we have to make sure that we have mutual exclusion. And for that, we're going to use this mutex. And to put threads to sleep and wake them up, we're going to use the condition variables. Okay, let's look at how programmers are going to use our lock once we implement it and give it to them. So let's say they want to write a function that reads from the database. They're going to acquire this lock as a reader. They're going to read the database. They're going to release the lock and get out. If they want to write a thread that is going to write to the database, they are going to acquire the write lock, write to the database, and release it. So this becomes critical section for the programmers who are going to use this lock. So these are critical sections that they want to protect. They want to have mutual exclusion. So they're going to use our lock to create this mutual exclusion in their programs. So we're doing service to other programmers. Now, this is the critical section that we don't care actually, right? We're not going to be concerned about this. Our concern is when we want to implement these functions, acquire lock. So let's look at one of them. So let's start implementing acquire read lock. Okay, so if a thread calls this function, we want to see if it is safe for this reader to have access to the shared data. So what do? We are going to look at the variables that we have. So those variables are going to be shared data. So we're going to we're going to lock the mutex because we're going to access shared data of this lock. So we lock the mutex. Now we check if there are other active writers. So if there is another active writer writing to the database, or if there are waiting writers, if some other writer has come and they're waiting, it means that I should wait. I'm not allowed to enter the critical section. I'm not allowed to acquire this lock, so I have to wait. So I become a waiting writer. Oh, sorry, waiting reader. So I add WR++, and I call on OK to read dot wait, and I pass the mutex. And at this point, I'm going to go to sleep because it's not a right time for me to acquire the lock as a reader. Once I wake up, if I wake up, now I'm no longer a waiting reader. So I do waiting reader minus minus, but I have to check again. As you remember, in condition variables, we have to have it in a while loop rather than if. So I check again if everything is okay. Then I become active reader. So if I get out of this while loop, it means that now I have access to the database. So I am now officially an active reader. So active reader plus plus. I then release the mutex and I'm done. So just note that this mutex, we're just using it for our critical section. So this is a critical section for us. This is not critical section for the database. This is critical section for us who are implementing acquire, read, acquire, write, and stuff like that, right? So that's where we're using this mutex. The programmer has no idea that this mutex exists. So don't, all of a sudden say, oh, why are you releasing the mutex? Why are you unlocking the mutex when somebody is gonna go and read? Because this mutex has nothing to do with that database. These variables are the ones that we're using to ensure that this reader-writer lock behaves the way it should behave. So as you can see here, if there are other active writers, if there are other active readers, we're not going to wait, right? So let's say there are 5 other readers. So if AR equals 5, I'm not going to wait. So I will be fine with going and acquiring this lock as the 6th reader. Now let's look at releasing the reader lock. We're going to lock the mutex. We're going to do AR minus minus because we're done becoming a reader. So that's why we have called release the lock as a reader. So AR minus minus, no longer we are a reader. So we're going to check now to see if there are no other active readers. So if we are the last reader, and if there are some writers waiting, then we can signal them. We can tell them that you can now go and try to acquire the lock. So we do OK to write that signal. So again, this happens only if we are the last reader and if there are writers waiting. And otherwise, we're done. We just do AR minus minus and we get out. And before getting out, we release the mutex. Now let's look at acquiring the lock as a writer. So again, we acquire the mutex first. We check to see if there are any other active writer or active readers. So if there are other threads that are writing, at least one of them, or there are readers that are reading, then I should not continue. I should wait. So then I become a waiting writer and I call OK to write that wait to wait. Once I wake up, I probably have received the signal. So I'm no longer waiting writer. I check again to see if everything works. Then if this check doesn't fail, then I become active writer. So active writer plus plus, and then I release the mutex or unlock the mutex. Now let's look at releasing the lock as a writer. You lock the mutex. You are no longer an active writer, right? So active writer minus minus. And now you have to check. So if you are a writer, right, and you're done, now you want to see if there are other writers waiting or if there are other readers waiting. And if there are, you can signal them. So here is if there are waiting writers, then signal them. So OK to write that signal. If otherwise, if there are waiting readers, then signal them and get out. Although there is one thing here, we can use broadcast, right? If, let's say, if there are no other writers waiting, and there are a bunch of readers, now we can broadcast, because all of them actually can go and start reading, because it's okay for all of them to go and read. So you can compare this with the signal we used for writers, because for writers, only one of them should go and write. So we used signal here. But for readers, if there are no other writers, then all of them can actually go and start reading. Okay, so that's it. So we have implemented it. So we're kind of done with today's lecture, although there are other slides. So we're going to analyze it now. So before that, let me answer questions that you've asked. So I'm a little unclear on what a monitor is conceptually, aside from a mutex and at least one condition variable. Would you mind clarifying that point? So a monitor is going to provide for us mutual exclusion and scheduling constraints. The same thing that semaphore does. So monitors and semaphores, both of them do the same thing. They provide mutual exclusion and scheduling constraints. And when I say scheduling constraints, I mean things like, here when we want a writer to wait or a reader to wait and get signal or things like that. So we want some order to be implemented. So a monitor and semaphore do that. Now semaphore does it with just one object, and that is a semaphore. You can use a semaphore for mutual exclusion, and you can also use a semaphore for scheduling constraints, as we saw during the lectures. Now with monitors, you have to use two different objects for each. So if you want mutual exclusion, use a mutex. And if you want to do a scheduling constraints, use condition variables. So as long as you know what condition variables are, you should just be fine with the definition of a monitor being it's a mutex and zero or more condition variables. Would it be okay to signal even if there are no waiting writers? It won't break anything, right? Yes, it's fine if you want to send a signal even if there are none. Actually, if you wait a little bit, you will see it in the slides. So I have it when we start analyzing, yes. Okay, so another question. Are waiting writers given higher priority? Yes, actually we will talk about priorities and starvation and all of that. So that's the analysis that is going to come. So if you don't get an answer on this question, come back and re-ask it. Why do we pass the mutex to the CV on wait? I discussed this in details yesterday during the lecture. So just visit, either visit the slides or watch the lecture. So it has something to do with this wait function. So wait function has to release the mutex, unlock the mutex, and then go to sleep. Because if you don't release the mutex, like if let's say if this was not here and you had only a wait function and this wait function puts you to sleep, then nobody else can then lock the mutex to check the internal state of your lock. So all the other threads would get blocked. So nobody can do anything, right? That's why we pass it inside wait to be released. And then wait, once it wakes up, it reacquires, relocks the mutex before returning, which again we discussed yesterday. Okay, Now let's ask some, before I actually analyze it, let's run an example here. Hopefully that this example will give you some more insight into this. So right now what I've done here is this is the acquire. This is the spell of acquire is hard. Acquire reader lock. This is the release RL. This is acquire writer lock, and this is release writer lock. Yeah, so my dictation is the worst. Okay, so I just you know, I just, instead of using those function, I put the code here. So this becomes the critical section. Critical section for programmer who are going to use our code. So these are the critical sections. Now for us that we're implementing this section between these two mutex, these are our critical sections where we want mutual exclusion in our code. Now let's run an example. So let's say initially the lock is initialized and it's fresh, everything is 0. So there are no active reader or waiting reader or active writer or waiting writer. So everything is 0. Now let's say R1 comes. So this is reader 1. Let's run through the code that it's going to run. So it's going to call the acquire reader lock. It's going to lock the mutex. It's going to check for active writers or waiting writers. There are none. So both of them are 0. So this becomes a first active reader. So now we increase active reader to 1. So now we have 1 active writer. So at this point, this guy goes and starts reading. Now let's say while R1 is reading, doing whatever he wants, so reading different databases, whatever, let's say R2 comes. Now R2 comes, R2 tries to lock the mutex. It can do it. Checks for active writer or waiting writers, there are none. So again, this guy becomes the second writer. So now we have 2 writers, sorry, second reader. So now we have active reader equals 2, and we're good. Now this guy enters the critical section of the programmer, starts accessing the database safely. Now there are 2 readers accessing the database, both of them simultaneously, and that's good. That's what we wanted. We wanted 2 readers or more to be able to read simultaneously from the database, and this implementation is giving us that. Now let's say a writer comes. So at this point, writer 1 comes. What does it do? It locks the mutex. It checks and it figures out that there are active readers, right? There are no active writer, but there are active readers. So AR is 2. So it's more than 0. So it becomes a waiting writer and it goes to sleep. So it calls on OK to write .wait. So now we have 1 waiting writer. So it just does that. It releases this mutex and goes to sleep. Now let's say at this point, reader 3 comes. So the third reader thread comes. So it acquires the lock, and it's able to do this because the writer W1 released the lock and went to sleep. If it hadn't released the lock, now R3 would get blocked. But because mutex is unlocked, so the R3 is able to lock the mutex. Now it gets to this condition. Now it checks for active writers. There are no active writers, but there are waiting writers. So this is one area that we're prioritizing writers to readers. Now, you might say it is safe for this reader to get access to the database because there are only 2 other readers accessing the database. Now I can become the 3rd one. And that might be true. So in one implementation, you might want to allow this to happen. But in this particular implementation that we're thinking and we're analyzing, writers have higher priority over readers. So at this point, although there are no active writers, and it might be safe for this reader to go, but because there is a writer waiting, so we're not going to allow R3 to go ahead and access the database. We're going to make R3 to wait. So that's what's going to happen. Now we have a waiting reader, and this guy goes to sleep. So it calls on OK to read that wait. Now, let's say now R2 is done. So R2 is done with its reading of the database, and it wants to get out. So it starts executing the release read lock function. It acquires the mutex, which is fine because R3 has released the mutex before going to sleep. So this guy is now able to lock the mutex. It checks. So AR minus, so now we have 1 active reader. So we're not the last one, so we don't do anything. So R2 gets out without doing anything. It just decreases active reader. Now let's say R1 now wants to exit. So it also decreases AR. Now AR is 0 and waiting writer is 1. So this condition is met. So then we send a signal to a writer. And in this case, we only have W1 waiting. So at this point, we're going to send a signal to W1 and make its state ready. So the state of W1 was waiting. Now state will change to ready. We don't necessarily start executing it. We just put it on the ready list so that the scheduler can actually schedule it at some point. Now we get out, right? Now, let's say there are no other threads in the system, so the operating system picks W1 to execute. W1, who received the signal, now is no longer a waiter, but it has to check. So after this line, it's going to go up, check again. And it figures out that there are no active writer, there is no active reader, so I'm fine to go. So we get out, we become active writer. So AW becomes 1. We have 1 active writer. It gets into the critical section, and let's say it's done. So it wants to get out. What does it do? It's no longer active writer. Now it checks, are there any other active waiting writers? In this case, no. So that's fine. It checks for active for waiting readers. There is one. So this is R3 who got blocked. So now we can send a signal to that guy. In this case, broadcast, but there is only 1. So that guy now wakes up. We exit. Then R3 is going to wake up. He wakes up inside wait. He gets out, decreases the number of readers, goes up, checks this again. Everything is fine. It becomes active reader, and so on and so forth. OK, so this was an example. We just ran through our code to just show you how it works, right? Hopefully that clears this a little bit more. In terms of our implementation and how it's going to be used by the user programs. OK, now let's analyze this a little bit. Let's say, what if I didn't put this line? So this is a question that one of you guys asked. What if I just, signal without checking this? Let's say I don't check any of this. I don't check if I'm the last reader, or I don't check if there are any other writers waiting, and I just send a signal, would this change the correctness of my program? I usually would pause here and let you guys answer. Unfortunately, we're not in person, so I'm going to answer it myself. The answer is no. It does not make our implementation incorrect. So our implementation remains correct. So correctness-wise, we're fine. But in terms of performance, it's actually wasteful to send this signal. Why? Because if you're not the last reader and you send a signal to writers, let's say there are other writers, so one of them wakes up, so they're going to wake up here, eventually get scheduled, and there's a high chance that they will check this again and they will find out that there are other active readers. So they would put themselves back to sleep. So you just did unnecessary work, and that unnecessary work will decrease the performance of your system. So that's that. So correctness is fine, but performance, we're just doing wasteful operations. Now, what if I broadcast instead of sending a signal? What if I wake up all the writers? Would the correctness of my program be compromised? And the answer is, again, no. So your program will stay correct. However, again, you're going to be having a bad performance. The reason is you're going to wait a whole group of writers, and only one of them will get out of this while, because only one of them is allowed to get in as a writer, and the rest of them are going to check and see there is another active writer, and they're going to go to sleep. So you introduced a lot of extra work that was not needed. So you should only wake up one writer. If you wake everybody up, only one of them is going to eventually get in. So the rest of them are going to put themselves to sleep. So you woke them up and then they put themselves to sleep, and that was unnecessary. So performance degrades, correctness is fine. What if, now it's another question. What if, so right now I have two different condition variables for readers and writers. So readers wait on OK to read condition variable, and writers wait on OK to write. So I have two. What if I just change it to one? What if I have just one condition variable that says OK to continue? Would that make my implementation incorrect? So maybe I give you a little bit of time to think before I answer. Okay, now this one actually does make your implementation incorrect. Why? So let's go back to the example we saw. In that example, W1 was waiting on OK to write, and R3 then came and waited on OK to read. So W1 was waiting on OK to write, and R3 was waiting on OK to read. Now, if I don't have two separate condition variables and I only have OK to continue, then both W1 and R3 are going to wait on this. Now, let's say R1 and R2 are done and they want to send a signal. If they do this signal, if they do OK to continue dot signal, so let's say R2 first got out and then R1 got out, and R1 looks and sees that there are active, there are waiting writers, so it sends a signal to okay to continue. Now, when you send a signal, there is no guarantee that it will be delivered to the first one that waited. It can deliver to any of the threads that are waiting. And it's possible that you deliver the signal to R3. Now, if you do that, R3 is going to wake up. So where does R3 wake up? R3 will wake up here. And then it has to check again. So what does it check? It checks and sees that, oh, there is another waiting rider. So it again calls wait and goes to sleep. So you temporarily remove R3 from this list, but then R3 puts herself back. Now, as a result, this signal that you sent got wasted. So now if there are no other readers coming, so if in future all the new threads that are coming are actually any thread that comes now, so a writer comes or a reader comes, what's going to happen to them? I guess a writer probably can go in, right? Because the writers are not going to search for active writer, but generally speaking, there is a chance that you have a deadlock. You will not deadlock. You will have a starvation. So if in future, let's say there are no other threads to come. Actually, let's say these 4 threads were the only threads that you had. Now, R3 and W1 are going to wait forever in this implementation. So they're going to just starve forever. Nobody is going to come and wake them up, right? Because this signal got wasted. Because this signal was delivered to a wrong person, and that wrong person put herself back to sleep. So the signal got wasted, and therefore this implementation is incorrect. You still don't allow, bad things to happen in terms of mutual exclusion, right? Because whenever you're talking about these problems, you have to consider it's kind of like the too much milk problem that we saw. We need 2 properties. The first property is that you want mutual exclusion, meaning that you don't want this to be unsafe for 2 threads to have unsafe access to the data. You also want liveliness. You want the system to continue working. So you don't want a starvation. So this implementation actually gives you a starvation. So it still keeps your system safe, meaning that it doesn't allow 2, for example, writers to access the database, or a reader and a writer. But when it comes to liveliness, this is not. Excuse me. This is not going to be meeting the liveliness property. I got a question. So if signal doesn't always signal the earliest process in the waiting queue, then what heuristic does the OS use to signal processes? I thought queues were first in, first out. So first of all, we haven't yet talked about how to implement this, right? We haven't talked about the internal of a condition variable. Now, you could potentially have a condition variable that ensures first come, first serve. So if you're the first who waited, then you're going to be the first one who is going to be signaled. But that's not guaranteed. If you're using different thread libraries, that's usually not guaranteed, right? Even if that was guaranteed, right? Even if that was guaranteed, it could be that we have W1, R3, and then W2, maybe, right? So then R3 would get the signal instead of W2, and you would have the same problem. Let's say W1 goes, and now R3 and W2 are here, and then you would have that problem. But again, generally speaking, you should not make any assumptions on the order of signal. So usually the thread libraries who provide condition variables only provide features like if you are waiting, you will eventually get a signal. So if there are signals coming, infinite signals are delivered, then you will eventually wake up. They don't, it's, you know, it's hard to, if you are going to implement a thread library and you want to implement condition variables, it's going to be hard to provide these guarantees that you have first come, first serve, right? So most of the ones that I know, they don't guarantee anything. They just say that if you're waiting and if there are enough signals, then you eventually will wake up. But there is no guarantee on the order at which you're going to wake up, okay? Now let's continue. What if I still have this OK to continue, but instead of just using signal, I change everything to broadcast. So I broadcast here, which was a signal, and I broadcast here, which was a signal. Now this implementation actually works, so it's now correct, because the problem in the previous implementation with one condition variable was that the signal might have been delivered to a wrong person and get wasted. So instead, you can use broadcast. Now this implementation will work. It's correct, but again, it's really inefficient because you're going to wait everybody, and only one of them is going to be using the signal. So this is correct, but really bad implementation in terms of performance. Now let's ask another question. Does this, under this implementation, do readers starve, or is it possible for readers to starve? The answer is yes. Unfortunately, this implementation, as we discussed, prioritizes the writers. So writers are going to get more priority, so they could, in fact, starve readers. So let's say you get writers very frequently, then the readers are going to just starve because there is always either an active writer or a waiting writer, and both of them have higher priority than a reader. So then your readers would starve. So you might actually have less writers than readers, but if the frequency of your writers coming to the system is high, then your readers could suffer. So you would probably only want to use this implementation if you have a system where writing to the database is very infrequent. So you infrequently write and very frequently read. Then this implementation is good because you probably want to, you know, if you have like one write every 1 million reads, then you probably want that one write to come, change things, and then go and give it high priority to just get done with it and then do your readings. But if you have a system where writes are very frequent, then you probably don't want to use this lock. You have to change and tweak this implementation to probably have some balance between writers and readers or something like that. What about writers? Can a writer starve in this implementation? Oh, by the way, am I done? So I think we're over time. Let me check. If I'm not mistaken, I'm done. If that's the case, that's bad because SE 350. Yeah, so I'm done in terms of time, but unfortunately I am not done with this example. So if you have to go, and the video will be posted, so you can come back and see what happens after this. I will try to be as fast as possible to finish this, but this example is important. So can writers starve? And the answer to this question is yes. How can a writer starve? Here is an example. So let's say W1 came and started waiting. So this is okay to write. And W1 is waiting here. Now, R2 was done R1 is done. Now it sends a signal to W1. Now W1 starts running. Sorry, doesn't start running. So now W1 becomes ready. But it doesn't run, right? So then R1 finishes. So now let's say we're done with R1. Now, before R1, right after R1 is done, let's say W2 comes in. So now W2 comes in. This is a new thread. It hasn't yet ran. So it also becomes ready. So now on the ready queue, I have W1 and W2. And let's say a scheduler picks W2. It's possible because the scheduler can, schedule W2. Now W2 starts running. It goes and it checks there is no active writer or active reader. So it becomes the active writer. And now let's say at some point there is a context switch. Let's say the timer goes off and we context switch to our W1. Now W1 wakes up from here, starts running. It goes and checks and it figures out that there is another active writer. So then it puts itself to sleep. So then W1 goes back and waits. Now let's say W2 is done. So then it signals W1 again. So W1 again becomes ready. And let's say W2 is done. But right before we context switch to W1, let's say W3 comes. Now, again, a scheduler has to pick between W1 and W3, and there is no guarantee that the scheduler will pick W1. The scheduler could, again, pick W3. So now W3 goes, it starts running, and then W1 goes back to sleep, and this could continue forever. So there is no guarantee for W1 to eventually run. So this implementation does not guarantee that a writer will eventually get to acquire the right lock, and it could starve. Now, how do we fix this? One way to fix this, you might think, is like banks, or some, if you go to get your driver's license, or you go to this Service Canada or something like that, they give you a number when you get inside. So you press a button, you get a number. So this is your number. Now we're going to act like this number is going to be your turn, right? So we can try that. So we can, instead of, actually the first one to try before actually those numbers, sorry, I got ahead of myself. So one thing that we can do for acquire write, we can put this wait for writers here to check if there are waiting writers. Then we will wait again. But you can convince yourself that this doesn't actually work. I'm not going to tell you how, but then go and convince yourself that this doesn't prevent the problem that I just described, that a writer could starve. So this is not a good solution. Now, the second solution is to use those numbers. So we're going to add to this active reader, active writer, active, waiting reader, waiting writers, those 4 variables. We can add 2 more variables. And that would be a number of writers. So this shows us how many writers so far have come. And then another variable that will show us who's next. So next to go. Who's the, like, this is basically the number you see in when you go, for example, in Service Canada, they say, okay, next number to come to this to get service is number X or Y. So this is next to go. Now, this is an implementation using those 2 variables. And again, I don't have, unfortunately, time to analyze this, but if you look at it, you can prove that this actually doesn't work. So this implementation also doesn't work because there is a possibility that the signal will be delivered. So when I call OK to write signal, so this signal is going to be given to a writer, and this writer could wake up because this signal is not guaranteed to be delivered to the first writer who waited. Then this writer could be a wrong person to receive the signal. So they check again and they figure out that it's not their turn and they put themselves to sleep again. So this signal will get wasted. And we saw another example where a signal got wasted and we had a starvation. So this also gives you the same problem. Okay, so what should we do? How can we just, get this first come, first serve implemented without relying on the condition variable to do this for us? The idea, which is a very famous idea, is to use to make every writer have its own condition variable. Instead of having this OK to write condition variable and put W1, W2, W3, so on and so forth on them, and then send a signal which we don't know where it's going to be delivered, we can make every writer to have its own condition variable. This guy will have condition variable 1, this guy will have condition variable 2, this guy will have condition variable 3. So everybody will wait on its own condition variable, but then we can put these condition variables in a queue. So we can have our own first come, first in, first out queue. And then when you create your CV, you can put that CV in this queue. Now, if we make sure that this queue and these condition variables are created in a mutually exclusive manner, so this queue becomes a critical section again for our code, then we can just look at the head of this queue and find that condition variable and send a signal exclusively to this condition variable. And because only one thread is waiting on this condition variable, we send the signal to the right person, and then we can have this first come, first serve. So again, unfortunately, I don't have the time, but you can actually look at the slides and see that that's basically what we're doing. So here by locks, I'm creating mutual exclusion. I create my condition variable, I put it in this queue, and whenever I'm sending a signal, I look at the head of this queue and I send a signal to the head of this queue. This way, I create this first come, first serve. So therefore, W1 will not starve because it will get the signal. Okay, sorry that I went over time, but hopefully this is an example that is helpful for you to understand condition variables more. Thank you for sticking around. Sorry I went over time. We'll see you tomorrow during the lecture. Take care, be safe. Talk to you tomorrow. Bye-bye.